Hello everyone, today we'll be discussing vectors, and kind of similar to the last section we saw, it's not the most difficult thing in the world, but it's just maybe a little new. In fact, this is a little different in some sense because this is not necessarily as visual as the last section where we discussed three-dimensional coordinates was, but we can make it visual if needed. And from my perspective, personally, removing the visualization actually makes it easier, but maybe I'm more of an algebraist, I don't know. But in any event, let's kind of cut to the chase. So a vector denoted V with this kind of arrow hat on top is a directed line segment. So that's what a vector is. It's just imagine it's basically an arrow. That's what you call an arrow. It has a tail end and it has a arrowhead end, like that. So in other words, vectors consist of direction and magnitude. The direction is basically the angle that it points towards, and magnitude is the length of the vector. So this is known as the magnitude of the vector. And in fact, just so we can get this out of the way, and I'll probably denote this later on, but if this is the vector v, then its magnitude is known as v in these kind of absolute value symbols. In fact, some books tend to use double absolute value symbol. We'll actually be using just the single one, but just know that some books may use the double absolute value symbol, just as not to confuse ourselves with the actual absolute value. Okay, so now, just to give you some example, let's try to kind of get a visualization here. So let's say we're going from one point to another point in a specific direction, and let's call that vector v. Now, if we have another vector that has the same length and same direction as v, but not necessarily in the same location, then these are considered equivalent vectors. So in fact, you can think of moving this tail end point to the origin and having the same direction and magnitude, and that can also be called v, which kind of seems a little weird because, well, we don't really have uniqueness here, but it's unique up to direction and magnitude. That's the really biggest thing I can say about vectors is they are direction and magnitude. Now, in two dimensions, we have two components. We have the x component and we have the y component. In fact, very often this is known as vx and vy, but in general, it just kind of depends on the notation. In fact, the notation we'll be using, we'll be calling the x component v1 and the y component v2. So more on that later. Now, as far as in three dimensions goes, it's the same exact idea. Now we just have one more dimension to play with, though. So imagine we're going, let's say, here, here, and down here. We try to project these in the xy plane first, and then down in the z direction. From the origin to this point in three dimensions, we have this vector v. And if we maintain that direction and magnitude in three dimensions and move it somewhere else, let's say like over here or something, we can have the same vector v, as long as it has the same direction and same magnitude. Now again, when I draw things in three dimensions, it becomes a little weird because it's hard to tell what I'm showing. But here we can clearly see the direction and magnitude appear to be the same. The only problem is it looks two-dimensional when in reality it's kind of meant to be sticking out this way like that. Okay. Now the so-called component form of a vector is written like this, where we have these so-called components, and these components, so this is what is known as an nth dimension vector. So you can call this n dimension. But for our purposes, we'll mainly be going up to 3. We can possibly see a 2-dimension vector. In fact, here we saw a 2-dimension vector, and here we saw a 3-dimension vector, but mainly we'll be talking about 3-dimension in this class. So we won't really be going beyond that, but you could go beyond that, and it's hard to visualize if you go beyond that, but algebraically it still makes sense, and we use the same rules. So more on that in a moment. But we often consider this the x component, the y component, and the z component. Okay. And then if you were to go beyond, then you'd have a 4th dimension, 5th dimension, and so on, which again becomes a little hard to visualize. Now, what these components represent are basically the lengths in that direction. And in fact, the best way of representing this is if you go from the origin. So from the origin to this x value, to that y value, to that z value, that represents that vector, where your tail end is the origin and your arrowhead end is this point, v1, v2, v3 in 3 space. Now, how you add vectors is you just add them component-wise. So if you have a vector u and a vector v, and vector u is u1, u2, u3, and so on, and vector v is v1, v2, v3, and so on, then adding these two vectors is just u1 plus v1 for the first component, u2 plus v2 for the second component, u3 plus v3 for the third component, and so on. You get the idea there. So not too much craziness going on there. It's pretty intuitive. Now, scalar multiplication is a little different. With addition, what we're really doing is we're adding these two vectors to obtain a new vector. With scalar multiplication, we are multiplying a number to a vector to obtain a new vector, which is kind of thought of as a stretch of the vector, if you will. So if this number was 2, then you'd be doubling the length of the vector. Direction stays the same though. So notice this number c is just any real number. So this is a number in the real, so this is in the set of real numbers. Just a regular real number. By the way, here all of these components are real numbers as well. So v1, v2, v3, all the way on, they are some real numbers. But here we're multiplying a real number to a vector, and all that does is essentially distribute this amongst each of the components. So we get c times v1, c times v2, and so on. That's really all I want to say there. Now there are visualizations, and I kind of spoke about the scalar multiplication one. The addition one's a little harder to describe in 3 dimensions. We'll possibly do an example in a little bit involving 2 dimensions, but long story short, when you're adding 2 vectors, basically you're considering a parallelogram created by the 2 vectors. So if this is u and this is v, for instance, so that's v and that's u, for example, then you can create a parallelogram by essentially copying v or u over to v like this, and copying v over like that, and where the tail of one hits the head of the other, so imagine going like this to this, then the diagonal of this parallelogram ends up being the sum of the 2 vectors. Now I've shown this in 2-dimensional space, like in on a 2D plane, but the same is true in 3 dimensions. It's just kind of hard to draw again just because of the nature of drawing 3 dimensions on a 2-dimensional surface. But hopefully this kind of gives the idea. And again, when we get into an actual example of addition, I'll try to show that. Another thing I must say is that scalar multiplication, the scalars could be negative. Now when you're multiplying a number by a negative, or multiplying a vector by a negative number, the negative symbol swaps the direction. So instead of going, let's say, in a certain direction like this, in fact, let me just show you, this is v, okay? The negative v will have the same direction and magnitude, well, it has the opposite direction, but the same magnitude. So it's basically like the tail and arrow head end swap. So that's what negative v is opposed to just the vector v itself. So I hope that part kind of makes sense. And now we're going to move on to actually see some examples, and then from there we'll look at some properties of these. All right, so now here we have, like I discussed earlier, the magnitude or length of a vector, and we have the actual calculation, and it's just literally the square root of the sum of the squares of the components of the vector itself. And again, mainly we'll be looking at a 3-component vector, but it's true for any component for that matter. And also you can see for 2 as well. Now the calculation for 2 and 3 is pretty simple. It's just kind of geometry reasoning to find the length of a vector. So I'm not really going to discuss it too much, but just for instance, imagine in 2 dimensions, if you have this vector v, whose x component is v1, and whose y component is v2, then you can create a right triangle whose lengths are, well, v1 and v2, and then by, well, Pythagorean theorem, the hypotenuse must be the square root of v1 squared plus v2 squared. So that's not too bad. And there's a very similar reasoning for 3 dimensions, but it's a little more to do there. Essentially what happens is if you have, and again, it's kind of hard to draw just because it's in 3 dimensions, but if you have some vector v sticking out here with certain dimensions, again, it's kind of hard to draw, but what you end up doing is you end up getting this, this kind of projection onto the xy plane, and that ends up being the hypotenuse that we found here, and then you can use that with this dimension, the z dimension, and you end up getting that after you square that, the square root goes away, and you end up getting this exact same calculation for the length of that vector v. And I think it's a pretty good idea for you to try this on your own. If this didn't really help, sometimes what helps, I think, at least for me, is to draw a box. And very often what you can do is you can actually find the diagonal of the box. And the diagonal of the box really just represents the length of the vector going from, let's say, the origin here to some other point. I don't really do that all that great, but you get the idea. That looks a little better. And you can kind of see what I was saying, that if you project to the floor of the box, and try to draw this in black, you end up getting this guy here, which is the hypotenuse of this right triangle, and then you kind of get this right triangle that's embedded inside of the box, which again is kind of hard to visualize, but if you try to do it on your own, I think it'll definitely help. Obviously try to draw a bigger and better picture, maybe that helps. But in any event, let's move on to this example where we're given these two vectors A and B, and we want to find these 5 different things now. So the first one we need to find is the magnitude of A, which we just discussed. So how do we find the magnitude of A? Well, it's clearly just going to be the square root of the sum of the squares of its components, which is 4 squared plus 0 squared plus 3 squared. Okay, and that's of course, well, 16 plus 9, that's 25, and the square root of 25 is 5, so the magnitude of A is just 5. Not too bad. And again, all that means is that the length of this vector is 5. Good. Now, how do we add A and B? Well, we just add their components. So this is going to be pretty straightforward. We're just going to look at the first component, or x component of each, and add those. Notice in this case, 4 plus negative 2 is the same as 4 minus 2, which is 2. Then for the second components, 0 plus 1 is 1. And then finally for the third components, 3 plus 5 is 8. So that's it. That's how straightforward addition is. Now subtraction we haven't quite gone over. But really what we're doing with subtraction is we're thinking of this b as a scalar multiple of, or this negative b, as a negative 1 scalar, as a number scalar, multiplied by the vector b. So in fact, you can think of this as a plus negative 1 times b. Now that's a little easier to see because negative 1 times b, if you scale a negative 1, that just multiplies each of these components by negative 1, hence changing their signs. So now this becomes 2, negative 1, negative 5. So I hope we all see how I'm getting these values. Just multiply negative 1 to each of these, and then adding that to the original a, which has not changed, 403. Okay. And now finally we can add component-wise. So 4 plus 2 is going to be 6. 0 plus negative 1 is going to be negative 1. And 3 plus negative 5 is going to be negative 2. Now something that you may be thinking is, couldn't we just subtract component-wise? And yes, you can. That's a different way of thinking of it, but that also works. Notice 4 minus negative 2 is 4 plus 2, which is 6. 0 minus 1 is negative 1. And 3 minus 5 is indeed negative 2. Something that comes to mind that I probably should have mentioned earlier is books tend to not use this arrow hat notation. They instead use a bold notation, which is terrible when it comes to actually writing it on the board because it's hard to distinguish a vector versus a scalar. So I'd have to draw this A like really bold-wise. And for example, something like that, that 2, for instance, would be non-bold because it's not a vector, it's just a number. And that becomes pretty hard to, in fact, I forgot the arrow even. But yeah, that becomes very hard to display, especially on the board and also on paper as well. So for that reason, we adopt that arrow hat notation, which books don't really do justice very well for some reason. It's probably because it's probably a bit of a pain to type in the arrow so much, opposed to just making it in bold. But it should at least state that, which I don't think they very often do. It's kind of up to the instructor. So here I am. So now 3 multiplied by v is just scaling in the number 3 into the vector negative 2, 1, 5. So we know how to do that. Just multiply each of these by 3. So it's basically distribution. And we get negative 6, 3, and 15. And that is the answer for part 4. For part 5, this is kind of where we have to not only scale and multiply to each of them, 2 to this one and 3 to this one, but then add those results. So let's see, we get 2 scaled to 403 plus 3 scale to negative 2, 1, 5. In fact, we already did the latter, the last one that is. We got negative 6, 3, 15, that's fine. And now the first one, multiplying each of these by 2 is pretty simple. We get 8, 0, and 6. And now adding these component-wise to the ones they correspond to, of course, we get, let's see, 8 times negative 6, or not 8, sorry, 8 plus negative 6, there we go. That's 2, 0 plus 3 is 3, and 6 plus 15 is 21, and there it is. So these are the vectors that result in those, and I mentioned that I would try to show the visualization as far as what these things represent, and it's very hard to do that on the board. It would be best if I were to do it with something in 2 dimensions, which I don't think we're actually going to go over an example of, because like I said, we want to mainly stick to 3 dimensions. Now, I'll try to do it with A plus B part 2. So I'm going to erase this and at least try my best to show you the visualization of what this means. And like I said, it's literally just grabbing this vector and this vector, connecting one of them to one of the tails to the head of the other one, and then connecting the far end tail to the arrowhead of the other far end, and then connecting to make a diagonal of a parallelogram. So let's take a look at that visualization right now. Okay, like I said, I'm going to do my best to try to graph this so we can see the visualization in 3 dimensions, and let's do it. So first remember that by the right-hand rule and by our normal convention of orientating these axes, I guess you can say, this is the x-axis, y-axis, and z-axis like we've seen before, so that's not too bad. Now I've made it 8 by 8 by 8 because the largest number I see here is 8, of course. Now vector A goes from the origin to 4, 0, 3. So remember, this is x, y, and z. So on the x component I'll go 4 units, on the y component I'll go 0 units, and then for the z component I'll go 3 units. Now where these actually connect is over here. So let's kind of try to draw a line, dotted line, that is parallel, that's supposed to be parallel to the x-axis. Okay, and then we'll kind of shoot up. So it's this point out here. And that's the point we're going to be going to. Now it looks like it's on the y-axis, but it's actually along this direction here outside. So I hope we can see that. Now from the origin, 0, 0, 0, to that point, that's our guy, that's our vector A. Now what about B? What does B look like? Let's see. So B is going to be negative 2 on the x-axis, so that's over here. 1 on the y-axis, which is over here, so let's project these first. So there we are on the x-y axis at that point. And then in the z-axis, we go 5. So if we project this over on the y-axis, and then, so it's going to look a little funny if I draw too many dotted lines. But this is over the y-axis, and then we have to kind of go out 2 in the x direction, so that's floating on top of here now. So let me project this up to the point here, and there we go, that's our guy. So this here represents the head end, arrowhead end, of the vector B from the origin. Perfect. So now what? Well, now again, it's a little weird because it's in 3 dimensions and it looks a little funny. But if we were to try to imagine moving B, so this is B. So imagine moving B so it's over here, not changing its direction or magnitude, and we get this kind of parallelogram. And imagine A, for instance, doing the same thing. And again, it looks funny, but it's supposed to be in 3 dimensions, so it's kind of twisted out, rotated out like that in 3 dimensions. Imagine. And A plus B should be the diagonal. So it should be the diagonal of that parallelogram in 3 dimensions. All right, so let's verify that's indeed the case. It looks like it may be the case, and my scaling may be a little off, but let's see. So we know that algebraically our answer is this, so our component values are 2, 1, 8. So let's see if this makes sense. So we'd have to go 2 units out in the x direction, 1 unit out in the y direction, so already we're at this point here on the xy plane, and then we have to project up 8 units. So if we project up 8 units, we land somewhere over here which sounds about right. It just looks a little funny because that would be like, I guess it would be like over here somewhere. So it looks like it would be more over here. My scaling may not have done that justice. I'm trying to think now why that is the case. So let's see, it's 403. Yeah, it looks like a mess because it's in 3 dimensions, like I said. Probably looks even worse, not in person, like how I'm seeing it. But yeah, if you were to go out 2, 1, and 8, 2, 1, 8, and up 8, you land somewhere here. I'm still having a problem with that. I wonder why that's the case. Oh, I see. So 8's over, look at this. So, okay, so it actually lines up perfect. For some reason I was thinking this is 8, but this is 8. This was an 8, that was 6. Or was that 6 or was it supposed to be 5? Yeah, so this is 6. It just looks weird because we got from here from 5 and then we went over 2 in the x direction, so it looked like we were on 6 on the z-axis. So it's a little tricky to look at. But if you were to go up 8 units from the z direction, so imagine this guy going over 2 units here, and then going out, and then going out 1 unit in the y direction, like that, we end up exactly at this point. Okay. So I know it looks kind of funny, but that's exactly what we end up getting. And this is projected from this point on the XY plane. Yeah, so it is a little daunting. It's like, I don't know if daunting is the right word of describing it, but it's a little bit of a mess, to say the least. There are some really nice 3-dimensional graphs you can play around with online. If you look up, for instance, like just 3-dimensional graphing or something like that, and Google that, for instance, you may be able to even find one that does vectors to allow you to visualize that more. And I think that would maybe help, but this is how you would do it by hand. It's a little bit to visualize, but that's why I say the visualization is one thing, but the algebra makes things a lot simpler. So now we're going to look and try to analyze our definitions of addition and scalar multiplication and getting some properties from that. So let's take a look at those properties right now. All right, so there's a lot going on here, but let's discuss the properties first. So there are 8 main properties, and these can all be basically verified just using the definition of addition and scalar multiplication with vectors like we saw previously. So we have commutativity of addition, associativity of addition, any vector added to the 0 vector is the vector itself, where the 0 vector, so let me write this here, is just the vector whose components are each 0. So imagine 0, 0, 0 or 0, 0 for instance. And for, like 5 dimensions, for instance, it's 0, 0, 0, 0, 0. But yeah. 4 would say that any vector added to its negative or any vector minus itself is the 0 vector, which certainly makes sense. This says that if you multiply a scalar to a sum of 2 vectors, that scalar multiplication distributes over vector addition. This says the opposite, that scalar addition distributes over vector scalar multiplication. And here this is associativity of multiplying the scalar to a vector. And here this says the scalar 1 multiplied to a vector A is just the vector itself. So these are all pretty obvious and you can verify these on your own. I don't think they're too difficult to verify. It's just, again, based on the definitions that we've previously established. Now we get into the standard basis vectors, which are I, j, and k. So it's just an alphabetical order, kind of like x, y, z, for instance. I is 1, 0, 0, j is the vector 0, 1, 0, and k is the vector 0, 0, 1. So what the standard basis vectors basically do is just represent a vector in a different way opposed to component form. So we can just write any vector as the sum of scalar multiples of these I, j, k vectors, and it ends up being the same. Now this is specifically for 3 dimensions. For 2 dimensions, you wouldn't even use k because you wouldn't have a 3rd dimension, you'd only have these 2. And you drop the 3rd dimension here. So in that case, I would be 1, 0, j would be 0, 1. And if you wanted to go 4 dimensions, for instance, it would be I, J, K, L, I guess, because that comes after K in the alphabet. Now, for this example, let's say that A is the vector I plus 2j minus 3k, where B is the vector 4i plus 7k. Then we want to express 2a plus 3b in terms of I, J, and k. And I haven't left much space here because it's actually very simple to do. And one thing that you can think of is this right here, I plus 2j minus 3k, really is just, and I can kind of write this off to the side just to show you. In fact, I guess I'll just do it here, it's fine. So notice I is just 1, 0, 0. J is 0, 1, 0. And 3 is 0, 0, 1. So if we scale and multiply and then combine these, and allow you to verify this on your own, but you legitimately just get what you expect to get, 1, 2, negative 3. Aha. So this really is just looking at the coefficients of I, J, and k, and those are the components of your vector. So really all we're doing is adding this vector to the vector 4, 0, because there's no j term. So you can think of this as plus 0j if you like, 7. So 4, 0, 7 added to this will be the vector, I guess it'd be 5, 2, and 4. So then the answer here would just be 5, 2, 4 with I, J, and k. And of course you have to write the vector symbol for each of those I, J, k. So that I don't think was too difficult. In fact, really we could have just done this by combining like terms. So for example, notice I plus 4i is 5i, 2j plus 0j is 2j, negative 3k plus 7k is indeed 4k, so this totally makes sense. And again, if you wrote I, J, and k out what they actually are for each of them, then you can combine each of these a's and b's into component form and then add just using our definition of vector addition. So everything I kind of showed there was using some of these properties. In fact, a lot of these properties. So I hope that part was okay and not too intense. Now the next thing to talk about are what are called unit vectors. And a unit vector is a vector whose magnitude is 1. So its magnitude is 1 unit basically, hence the name unit vector. Now for any vector v over its magnitude, in other words, 1 over its magnitude as a scalar multiplied by the vector v, is a unit vector. In fact, here we say that this is the distinct unit vector, you could say, that has the same direction as any given vector v. And we'll actually be taking a look at an example of a few of those right now. And beyond that, I don't think there really is much else to discuss in this section. Besides maybe applications, but that's going to make the video too long. So let's just take a look at a few examples of this, and I think that'll be the end for the video. Okay, like I said, this will be the last example we'll be seeing in this video. We want to find the unit vector in the direction of this vector, 2i minus j minus 2k. And I almost kind of spoiled it, but really we know this is the same as the vector 2, negative 1, negative 2. But again, just to show that, let me write it out, unlike I did in the previous example. I mean, I kind of did, but not necessarily. So let's see if we can do this. Like I didn't show the full detail, that is. So now if we scale in 2, we get 2, 0, 0. If we scale in the negative, for instance, we get 0, negative 1, 0. If we scale in the negative 2, that becomes a plus, like that became a plus. We get 0, 0, 2. And then if we add these finally, notice 2 plus 0 is just 2. 0 plus negative 1 plus 0 for the second component, let me double underline, is negative 1. And then 0 plus 0 plus 2 is 2. We indeed get what I said we would get here. In fact, I'm noticing now I didn't distribute this negative, which is why it wasn't entirely matching. That was my mistake though. Right, so generally doing it all out in detail like this kind of leaves more room for error, when in fact you could just remember this this fact, I guess you can say, that you look at the coefficients and those are exactly your components. Perfect. So now that we have that, we can find the unit vector by remembering that if this vector is called, let's say, v, for instance, so imagine we just label this vector as v, then the vector we want, let's call it u for unit, is going to be v divided by the magnitude of v, which remember just means that we are multiplying by the reciprocal of the magnitude of v. Now what is the magnitude of v? If this is v, then its magnitude is just the sum of the squares of its components. In fact, very often when you're doing this, if you want to do it fast, you can just ignore the signs, because squaring a negative will result in the same value as squaring the positive version of that number anyways. So I can just look at this and think 2 squared, 1 squared, 2 squared. So it's 4, 1, 4, which add to 9, and the square root of 9 is 3. So we'll get that here. 2 squared is 4, negative 1 squared is 1, negative 2 squared is 4. So we indeed get 9 like I suggested earlier, and the square root of 9 of course is 3. So this really is going to be, and again it's multiplied by the original vector v, and 1 over the magnitude, which is 3, times the vector v, which is 2, negative 1, negative 2. If we actually scale it in, then we get 2 over 3, negative 1 over 3, negative 2 over 3. So I would box this as my answer, but since we were given a vector in ijk form, let's write this in ijk form. And we know, based on our previous discussion, this is just 2/3 I minus 1/3 j minus 2/3 k. Perfect. And I'll box this. That's the answer for this example and the end of this video. So I hope you enjoyed this. In the next video, we'll be discussing dot products, which is just another thing you can do with vectors. It's going to be a whole lot of fun. I'll see you in the video for that. Thanks for watching, and see you then.